right, good afternoon. So, Lab 5 help. You've requested it, here it is. What do you need help with? Anyone want to start? Yep.
Could we go over like the library that you gave us and all the different functions?
Okay, library, we went over all the different functions and what we're supposed to do. Okay, so first off, we did lecture, 14, where we did the MMU simulator, where we essentially, go back to it. So this is what's given to you and what we kind of did before, setting up the page table so we can translate address ABC123. We can all see that, hopefully. So are there any questions about that before we start anything else? Because you should understand how that works first. So all good, we set up an L2 table, make sure the index points to an L1, L1 points to L0, that has our actual mapping, that points to the data, because we're using a 3-level page table here. So this is what it would look like just to set it all up that you don't have to do. This is just to set up, L1 or L2 points to L1, points to L0, points to a valid entry that has, in this case, read, write, set, and then it sets the root page table, which is supposed to simulate that register that's used for the actual hardware MMU whenever it does a translation. This is just purely simulating it so you can get a chance to manage page tables yourself, because the kernel does that and you're not allowed to do that. So we just simulate it in software. So this is like simulating it, changing what root page table the MMU uses, because it just points to a single L2. So this points to an L2. And then whenever we do, so there's functions that are just used for testing that simulate actually writing to an address and reading from an address. So in this case, we write to a virtual address ABC because we set it up so that that is actually a valid address. So we can see what we read to it, we can write to it, we can read to it to see that we actually wrote to it. And that's the default thing we're kind of given. So then the thing you could add is like, okay, well, let's test our fork copy. So what happens on a fork? Well, one thing that could happen on a fork is the new child has page tables that look exactly the same as the parents, but are completely independent in actual physical memory. So if the parent has an L1 or an L2 page table, I have an L2 page table. If it has a valid entry for index 0, I have a valid entry for index 0. And whatever index 0 points to, that L1 page table, if it has a valid entry for index 5, I have a valid entry for index 5. And those L1 page tables are, again, completely independent. Then same with the last step. So if it has a valid entry for index 188, I think ABC goes to, then I have a valid index for ABC, and it points to another page that's a different physical page of memory. So if one process changes, the value at that address, the other process doesn't see it, but it's valid because they're exact copies, they look exactly the same. So we're good with the kind of high-level goal of the lab. Okay, so API functions that you will have to use and you will find useful. So there's this header file. It has everything, you don't have to use everything. So they're kind of organized here. This MMU, all this MMU stuff is mostly used for testing, and this will be the only one you use because in the fork you need to know what L2 table to copy, and it's just whatever it currently is. So I would use this to figure out which L2 page table I need to copy, and that would lead me to copy literally everything else. Okay, aside from this, there are pages. So how this is simulating, what this is simulating is like when you boot up your system, you don't have any virtual addresses whatsoever. All you have is physical memory. So this is supposed to simulate all the pages are supposed to be like physical pages. So if you ask for a new page, it will give you a new physical page. But of course, this you're not managing the memory yourself. It's already done for you, but that gives you a new physical page. Free a page, same, just like new and free. If you want to deallocate something, well, you free it, and then you can use that page again for something else. You probably never even need to call this. This one's just used for testing to see how many pages you use, just a sanity check. So if you do a copy, well, if you were doing the fork copy and copying everything, if there are 4 pages in use by the page table, well, if I do a copy of everything, then there should now be 8, because I should have my own independent copy of it, and there should be 8 pages now. There's this get page table pointer. So these two are mostly used, you'll find useful when you're implementing the copy on write. So this will flatten a page, and essentially here you give it a pointer to a page, and it will give you an index for it, and it will be, the first page will be index 0, and then it'll go up to how many pages there are, which is in here. So there's max pages. So you can keep track of the number of references to a page by just making an array, and then you can get an array or an index. You can turn a page into an index. So you can, if you want to count the number of references to a page, you can make an array of size max pages, and then use these function, or like use this function to get its index. And then this just does the opposite. If you give it an index, it will give you a pointer to that page at the beginning of the page. So the page table ones, they are all set up. Our page table index will, given a virtual address and then what level you want to access, it will give you the index it will give you that index for that level. So for this, let's go back to, where is it? Main. So if we did that for like ABCD, or ABCD 1, 2, 3, well, if we split that between, my L1, L2, L0, then let's go here. Then it would look something like that. So if I give it, if I give it the virtual address ABC123 and ask for the index at 1, then it will spit out 5. If I ask for the index at 0, it'll spit out 188. If I ask it for the index at 2, it'll spit out 0. So that's a way to get that. No. And then this one will give you a PTE entry, and that will be a pointer to a page table entry. And a page table entry, remember, is that 8-byte thing, and you don't know quite exactly where the data actually is in that. It's just 8 bytes, and you have to use other functions to actually figure out the values, because if you actually just printed out the number, it might not line up with what you expect, so you should use the other numbers. So this takes a page table, so a page and an index, and then it will just give you a pointer to that index. Basically, it's just doing an array access and giving you the pointer. This one will do those two things in one step. So if you give it a page table virtual address at its level, it will directly give you a page table index, so you don't have to go through the 2-step process. It just uses one and then the other. And then these two things, PPN to page, will, given a PPN or a physical page number, it will just turn it into a page, like a valid pointer to a page, and it'll be aligned to a page. Basically, it's just going to shift everything over by 12 bits and make the offset 0. And then this will do the opposite. So given a page, it will convert that page to PPN number. And in this case, we're assuming like it's that RISC-V setup, so we're assuming a PPN is 44 bits. So it's a 64-bit number, but only the lower 44 bits are actually going to be used. And then all the rest of these functions take a page table entry, and they let you play with the bits. So this one will set the valid bit to 0, given an entry, which is just a pointer to a page table entry. This will set valid to 1, and this will return what valid is. So if I want to check if something's valid, I would call that. If it returns 0, it's not valid. If it returns 1, it is valid. And then the exact same thing for all the other permissions here. And then the last one is getting the PPN out of the entry because you're not quite sure where it is, and the other one's to set it. And then after that, we just have our 2 forks. So any questions about that? Okay, so let's start off a goal with the lab. So we can start it a bit. And should I do this first? Yeah. So just to be clear with what we're doing, so we're kind of assuming that we're given a certain number of physical pages. So in this case, if I called these our physical pages, well, say my memory starts at byte 0, which is actually a valid address, and I have 8 pages. Well, if I have 8 pages, I could call them page 0, 1, 2, 3, 4, 5, 6, 7, and that page number I'm calling them, that's the PPN. That's just the physical page number. So if I broke it down into the address ranges, because we're dealing with 4 kilobyte pages, page 1 will have valid addresses from 0 to 0FFF. Then page 1, 1000 to 1FFF, which is hopefully 4096 bytes, so on and so forth. So any questions about those pages whatsoever? So our page table entry, what it contains, it's just a number, it's 8 bytes, and it contains, what, 5 things. The PPN, which is 44 bits, which you don't know where it is in that 64-bit number, so that's why you have to use the helper functions. And then there's a custom bit that you can set at will, which you'll find useful for when you do copy on write. And then there's read, write, which are actually checked when you do that VMS write or read. So it actually checks that permission to make sure you have it. Otherwise, it generates a page fault, which you can optionally handle. And I guess we can see that. And then a valid bit, so to say that this entry is valid. And for new page and everything, by default, they're all 0 initialized, so everything is completely invalid. So any questions about that? Yeah.
Sorry, can you just go over again what the read and write bits do?
So the read and write bits, so if you're actually accessing memory, like from your L0 table, if you're trying to read to that, the MMU will check that it actually has read permission, so it's actually allowed to read. So if I tried to do, here, let's go back to, so yeah, we can just do it here. So first thing I do is write. Well, here I set permissions on that page with what I'm allowed to do. So if I do something like this, where I just don't set it, by default it will be 0, and if I do that, it'll say fatal page fault because you tried to access ABC123, and it gives you some more information like where the page table is. It'll say level 0, so the last access, and this was the page table entry itself. It's pointing to this page, which is valid, that's fine, and these are the flags. So read, it's read and valid, so write isn't valid, and I tried to write to it. Yeah, so that stuff's actually checked by the MMU. Okay, any other questions? Okay, well, I guess we can kind of start looking at it more. All right, so let's get started with, wow, please close, with fork. So if I were to start fork from scratch, well, we don't want to return just the root page table because that's essentially doing nothing, and you're making both processes share the same L1 page table. So if one changes memory, the other will change it. They'll see it. Nothing is independent anymore. That's really, really bad. So we want to use the parent one to copy from. So that's what's given by the new page table. So We can just name it better if we want. So that's the parents L2 page table. So we want to create a copy. So if we want to create a copy, we can call it child L2. So here we know we need to get a new page because we want to make them completely independent. So we need a new page. So we would need something. So we need a new page. And right now that new page is 0. So if we do something silly like just return it, well then it should generate a page fault because it has 0 valid entries. So let's go into main. So here I just added a call to it at the end so we can just play with it and test it. So if I go ahead and do this, so that should create a new L2 page table, and then if you're testing it to simulate context switching processes and like actually swapping the address space, we would do something like the testing code you're given does something like VMS set root page table, and we would set that to the child. Child. Wow, why am I root page table? So we do something like that. So now whenever we access memory, it's going to use the MMU, or the simulated MMU is going to use the new page tables we gave it. So now if we do something like, I don't know, let's try and write a 3 to that address. So if we do something like that, so we'll get a fatal page fault, and it'll say, hey, you're trying to write to this address. This is the page table, so that was the one we got from the new page. And it says it failed when it was trying to do the level 2 entry. So that was the first step it made, and it's saying our page table entry, well, it said that it points to the physical page number 0, which is not valid because that's like a null pointer, so it's not actually mapped in your process. And there are no flags, it's not valid, it's not anything, so there's no way it could work. All right, everyone good? Questions about that at all? Okay, well, I am not going to do this for you, but I will listen. So, in this function, if I want to see all of the valid entries in the parents L2 page table, how would I do that? Yeah. Yeah, so I can do a for loop of all the entries and just kind of check them out. So there's going to be 0, or we do a for loop, I starts at 0, it's indexed, and then I is less than, we have num PTE entries because there's a certain number of entries per page, right? All the PTE entries fit on a page. It's already defined for you, but we've done this calculation like 1,000 times. So this would be 512, but it's given to you, so you don't even need to know that. So we could loop over every single PTE entry. So the function we have to do that, to get an entry, is this one. So we could just get an entry from an index if we want to check it out, because we don't have a virtual address. We're just looking over the page table and just seeing what it has. So we would use this guy. And our page table we're looking at is the parents L2, because that's currently what we want to copy from, and our index. So now every time we will have a pointer to a PTE entry, and then we can ask questions about it. So if we don't ask questions about it, I did a little helper function here that will just print the PTE entry. So we can see. So what do we expect to happen if we actually run that now? Yeah.
Did we set like initially the read flags to 1 for all
So the comment was we set the read flags initially to 1 for all of them. So this is the parent table here. So it's L2. It got an entry for whatever this virtual address is and then set the physical page number to point to an L1 page table, and then we set the valid bit. So how many entries are in my L1 or my L2 page table? 1. And I'm printing out 512 entries here. So I should probably expect 1 to be valid and the rest to all be 0, right? So let's go ahead and sanity check ourselves. So if I do that, yeah, there's a lot of zeros, a lot of zeros, a lot of zeros, da, da, da. And then at the very top, hey, there's a valid one because the first index it uses was 0 in this case. So it's actually pointing to it's actually pointing to the L0 or L1 page table, and it's valid, so it would actually follow that, wouldn't generate a page fault immediately. Cool. So, all right, so what would I do if I just didn't want to print all of the stupid entries that are not valid? Yeah. Yeah, just check. If it's valid, I can do something like if not VMS was it PTE valid, and then surprisingly, it takes an entry. So I can do something like this. So if it's not valid, I can go ahead and ignore it. So if I want to just skip anything that's invalid, because I don't have to do anything if it's invalid, it doesn't lead anywhere. I wouldn't have to copy a page. I wouldn't have to do anything like that. So if I do that, whoops, yeah, so up here, I still have some other code. So up here, it just prints 1 page table entry because I only have 1 valid entry now. All right, anywhere else I should go with this? Yeah.
Now, because you're creating a copy, you need to put this entry on the child page table.
Yeah.
But first we need to allocate, like, because right now it's pointing to null. So first we need to allocate a new page table, right?
Yeah, yeah, so here, we can kind of pseudocode our steps here. So if there is a valid entry here, well, so if I'm looking at L2 entries and I find a valid one, it means it points to an L1 entry. And there's not going to be any tricky things where 2 L2 entries point to the same L1, because that would be weird and make your lives harder, and that's not the purpose of this. So if it's actually valid, then it points to an L1 entry, and yeah, we would have to make a new one because we want our own copy of that. So I need to make a new L1, and then I would point to it for this entry, and then I'd have to go through and then do the same, essentially do the same thing for L1, right? Any valid entries in L1, while they point to an L0, I have to make a new page for that, each one of those, copy it, make sure it points to that, copy, make sure the permissions are the same. In this case, it just needs to be valid, so not a big deal. And then when we get to the end, the L0 points to an actual page. We'd want to probably copy all the permissions and then make it point to a new page so that they're completely independent now. Yeah.
So it's like 3 nested for loops. 1 to copy L2, 1 to copy L1, 1 to copy L0.
So, yeah, the comment is 3 nested for loops. You could do that. I would suggest not doing that.
Okay.
Yeah.
Would you suggest creating like a recursive function?
Yeah, essentially you could, it'd probably be a bit cleaner if it was recursive and you just change the level. The only thing that's different between them is the level, right?
Yeah.
So and your base case is 0. At 0, I know I'm pointing to actual physical memory. So you could probably do a recursive thing for this. You could do 3 for loops, I guess, be really kind of ugly, and you'd be repeating yourself a lot, but I guess you could do that, which...
Can we use threads to say, like, once we come across that's valid, run a thread that copies it and at the same time move on to the next one?
Why would you need to do that?
For speed? I don't know.
Yeah, so like with the bank sim we did too, actually using threads for that makes it go slower. If I didn't, there's one thing that artificially slows it down, but these operations are so fast, the overhead of threads is too much, and there's like data races and stuff, so by the time you prevent everything, it's just way slower than just running on a single CPU. But yeah.
So in the L0 table, like the entries actually point to like the actual physical memory, so
Yep.
that should still be the same when you do VMS4 copy, right?
Uh,
Like the actual physical address it points to, should that be the same in the new page tables?
No. So here, let's go to this. Oops. So for ABC 123, how it's kind of set up is that, well, it just grabs a page. It says, okay, I'll use page 0. Let's see. I'll use this for the parent's L2. So it would grab that, make an entry for 0, and the PPN would point to an L1, and it would probably have a valid bit set. So the PPN would probably point to another one. This would be given as the L1 page table. It would have an entry for, what was it, 5. PPN, valid 1, points to another one. Maybe I use this page for L0. It has an entry for 180 whatever. And then this one actually matters for like read, write, and all the permissions. So it would point to the actual page. We had write on, read on, valid on, something like that, and then our data is stored there. So if we actually tried to access, you know, ABC 123, well, we would go whatever 123 bits and hexes into this page, and then there'd be 4 bytes there that we're going to treat as an int. All this does is just write ints to it. So it would, like, if we write a value of 1 there, it would just be in there. So what you should do is when you do a fork and you're just doing the first copy one, well, you're making a new L2 page table. It should probably have an entry for 0 that points to a different one. L1 has that same entry, points to a new L0. And then you're saying that, well, why don't we keep all the permissions the same here, or no, valid. And the PPN, we point here. Okay, so if we do that, say we are doing, so this would be, in blue is the child, red is the parent. So right now they point to the same data, and if the parent changes the value of, say it was, we called it X or whatever, so it changed X after the fork from 1 to 2, then if we change back to the child, what's the value of X? 2, which, is that what we want? No. So we need to do another copy here. So the only way this works is if we rewind, and remember, fork is supposed to be exact copies at the time of the fork. So, whoops. So I would have to, if the value is 1 at the time of the fork, I have to copy all the data that is on this and put it here, and then point to it. So now, if I try and change the value of X in the parent, it changes its value of X. If I try to change it in the child, it changes my value of X. But Where you actually start sharing the page, what you suggest is when you do copy on write. So that's the idea behind copy on write. So I try and share the page as long as I can, because if they're both reading, I don't have to actually make that physical copy of the page. I can just share it. As long as they're both reading, I'm all good. And I delay the write to try and, I delay the write as long as possible. So now if one of them tries to do a write, the idea behind that is, well, when you actually make the copy, so what we alluded to in lecture, when I make the copy, well, I can do something like this and just set the write bit as 0. So now if either one of them tries to write to that page, it is going to go and generate a page fault. So go here. So it will generate a page fault, and you are allowed to do things here. So you can modify PT entries here, you can allocate new pages, you can do whatever you want here. And whenever you return from the page fault handler, the MMU will retry the request once and succeed. So at a really high level, so you'll get into the details of why you need that custom bit set. So your tools are, you have a custom bit and you can keep track of the number of references to a page. But basically what you would want to do is change that write permission to 0 whenever a page fault happens in either of the processes, because either the parent's going to write that generates the page fault or the child. You don't know. You don't really care. You'll just be, the only page table you'll be able to modify is the one that currently generated the page fault. So let's just, for argument's sake, say the child did it. So the child tried to write, it generated a page fault, and it wasn't allowed to write. So I have to make it allowed to write, but I want to do it safely. So in the page fault handler, that's when you would stop pointing to this. You would get a new page, copy all the data. I guess you don't really have to copy the one you're about to modify, but that would be a pain in the butt. So then you copy the page, you change where the PTE entry points to. So it points to its own new page, and then you turn the write permission back on. And then whenever the MMU retries it, it can actually write to it, and it's a different page. Yep.
Do we have then to go to the other page table and turn the write on also?
So the question is, can I go to the other page table and turn the write on as well? And that gets to be the trick of it, because you won't. So whatever the page fault that gets generated is only for however it currently got there. So you'll have no way of knowing what other ones point to it unless you do like some really tricky stuff, but you don't need to do that. So yeah, so my suggestion is to keep track of the number of references to a page to know whether or not you should do anything. So if there's only one reference to a page, you have a unique one. So here you wouldn't be able to modify it, so its write permission would still be off. So one thing you want to be careful of is if I write through the parent now, if I switch back to the parent, and then I try and do a write to that address again, well, it's the only one pointing to that page now, even though it doesn't have write permission because it got turned off before. Well, now it's the only one pointing to it, so I can just actually turn the write permission back on. I don't have to do anything. So that's one of the tricks, yep.
So does the copy on write only apply to the last page, or in the L2, L1, L0 are still supposed to be different copies, or does the copy on write also apply to the L2, L1, and L0?
Yeah, so the question is, does the copy on write just apply to the data pages or apply to the other page tables as well? So copy on write only applies to the data pages, because if you actually shared page tables, then if you allocate new memory in one process, then the other process has it too, which would be weird. So it'd be a bit weird if you're running your program and then just new memory is available that got mallocked by another process that's supposed to be independent, and a whole bunch of other weird things can happen with that. So yeah, if they shared page tables too, not in this, but you could just, if you wanted to screw with another process and that was true, you could just free all your pages, and then it's freed for them too, so they crash immediately. Yeah.
Wait, you said keep track of the number of references to a page table, but we only have one bit to do that. So
So a page. So remember I said one thing you can do using, what is it? So using, what is it, pages? Using this, whoops, that's my bad. So using this to get index from a page, as I said, one thing you can do is just create an array of the number of references to a page because there are max pages, and it's supposed to represent physical memory, so it's not going to ever change. Like, you don't just shove more RAM in your machine and you can use it. At least, yeah, you have to reboot to use more memory. So you can just create an array that keeps track of the number of references to each pointer. And then if you want to turn it to an index, then you can use this. Yeah.
So if the parent and the child are like sharing one data page, and the parent tries to write to it, are we allowed to change the physical address of the parent as well, or only the child?
Yeah, yeah, you can, as long as it's safe to do so, you copy the page. Doesn't matter who started it, right? Yep.
One thing I was confused, I'm not sure if I misunderstood, but when you created like the new child page
Mm-hmm.
a while ago, you saw that like it pointed to like 0, 0
Yeah.
as the page. How do you make the page not point to 0, 0 anymore?
Oh, so the question is, like whenever wait, am I on this? Okay. So it was whenever I had this entry and then got the entry, it was all 0, 0, 0. That was your question?
No, when you did like the VMS new page.
Yeah, here?
Yeah.
Yeah. So
Is this a validator already?
So yeah, so when I do new page, it just returns the base pointer to the start of a page, and it's all full of zeros.
Okay.
So it's just 4096 bytes of 0, which, since valid being 0 means it's invalid, they're all invalid entries. Yeah. Yeah, so you can do, yeah. Other things, so yeah, I guess you could do 3 for loops in this if you really want. You might be repeating yourself a bunch, and then when you do copy on write, you do another 3 for loops. You can probably do better than that, but I guess I'm not your parents. Yeah, you could also just, instead of doing that, if you don't like the recursive solution, instead of doing like 3 for loops, just how about doing 2? So what about 1 for what level you're on, and then 1 for the entries? So that would probably be a bit better. Also, I mean, if you want to do what every programmer does, which is kind of, just looking at code, reading code, well, the MMU has to go through all of them. And you can see what it does. So it has a for loop that goes through the number of levels. Starts at 2, and it's defined. And then essentially we'll actually do the correct index because this is for a specific entry. But if you want to go over every entry, well, this is your loop per level, and then you'd have an inner loop that goes over every entry. So you could do it with 2 for loops if you don't like recursion. All right, any other questions, comments, concerns? Yeah. So if you've if you have multiple processes pointing all to the same page,
Yeah, so like the first time I only have one parent and one child.
yeah.
And they generate the page fault. And I correct that. And then after this correction, I had another copy on write, which points to the physical address of other parents or child. And then it generates a page fault again. Do you mean that at this time we have to exit the process or not?
No, so that's just describing what happens with the page fault handler. So the page fault handler, it will call it just on a single memory access. So on a single memory access, it will call it if it fails and generate a page fault, and then it will let you do something, modify the page tables as you wish, and then it will try that again. And if it doesn't work because the permissions weren't set or whatever, it will just actually exit the process for you. But each access is independent, so you're allowed to fix it up one at a time. Like, it doesn't happen just once.
Okay, so basically, if this page comes from a copy on write for function, then I should kind of fix this, have a new page table for the child or for the parents for the virtual address. But if that's not the case, I'm just gonna exit whatever the page fault is.
So for copy on write, like with this, when you're originally sharing, let's see here. So when we're originally sharing and we turn the write permission off, whenever someone tries to write to it, it will generate a page fault, right? Whenever it gets to the L0. So whenever it generates a page fault, you have one chance to fix it. So to fix it, that's when you like say the child did it. You should copy the page and then make the child point to it, turn on the write permission so that when it tries doing that again, it would actually work this time. Yeah, and then if it switches to the parent and tries again, well, the parent would now generate a page fault and wouldn't exit immediately because for every operation, you get one chance to fix it. So if it went back to the parent now and then tried to write to that same spot, here, if it followed through everything, the parent's write is also off. That would generate a page fault, and you can handle it. Yeah.
Also, we are also keeping the reference number, right? So if I just correct the child page table, so which means right now there are only one reference to the original child. Shouldn't I directly set the right to be valid for the parent process, for the parent page table?
Yeah, so in this case,
I will not even have a page fault when I have that virtual address for the parent page table.
so you would still have the virtual address. So when I went through and fixed it up here, so when the child tries to access it and I fixed it up and copied the page and set the write permission back, well, I didn't change the parents as part of that at all.
But can we update the number of reference to the physical page table? Because originally it was 2, and right now we correct it, and it's become 2 minus 1, and now it's 1. And then we can just set the original parent page table to be valid.
Yeah, so you would set the number of references, like refs, to 1 after that, but there's no way in your page fault handler you can figure out every process's like L2 page table that eventually has an entry that points to it. Because like this is an entry you would like just to turn the write permission back on, which is currently off. You can't just go change another process's page table. Well, you shouldn't, because you can just wait, right? I can wait, let the page fault happen, and then I'll notice that, hey, my write permission's off, but hey, I'm pointing to a page that I have the only reference to, so I just turn the write permission back on, and then it works. Yep.
Oh, what's the API for handling the page fault? Is it a signal, or does it automatically go to that function for us when the page fault happens?
Yeah, so when the page fault happens, it immediately calls this page fault handler.
So there's no need to like register a signal or.
No, this is all simulated, so the kernel doesn't care, right? I'm just writing a program that just allocates a bunch of memory and simulates an MMU. Like the kernel has no way of knowing what the hell we're doing here, right?
So your MMU library calls page fault handler.
Yeah. Yeah, so if you look at the code, which like is pretty much the MMU sim we went out, except that I have a page fault. It calls a page fault. So one of the functions says that if it should generate a page fault, and then if it does, if it hasn't faulted before, it will call page fault handler. And if this is the second time calling it where it's faulted before, it will say, yeah, too bad, and then exit. So this is, yeah, so this is where it happens. It literally just calls your function. But yeah, if you actually did this on real hardware, it would generate an interrupt. So there would be a page fault, which would be an interrupt, but this is just like a software interrupt. Well, it's not even really an interrupt because I'm calling it directly. But it's supposed to simulate like a page fault interrupt. Yeah, a page fault interrupt that you have no choice not to ignore. All right, any other questions? Or go over the test cases or whatever. So yeah, I added 12 test cases now based off feedback to make sure that we have done it correctly. So yeah, so for all this code, like you should just call that get root page table once, because that's what you're copying from. That's it. Don't call set page table, root page table at all, because that's meant to simulate actually context switching. You're not supposed to do that when you're just setting up page tables and all that stuff. But most of the other functions you should know how to use. Yep.
Both functions are returning just the child L2, right?
Yep. Yeah. For both of them, you're just returning the new child L2. Yeah.
So, and the other thing is, so the second idea is that we use like call optimization.
Yep.
But call optimization only happens when we have the page fault. So it doesn't happen when we actually call the VMS fork page, right? Because when we do the VMS fork copy and write,
Yeah.
it still don't know if we'll run into like some page fault.
Sorry, what do you mean? So,
Where do we write the page fault handler?
so you write the page fault handler just here.
Okay.
So this actually is called on a page fault, like. So right now, the main I have, right, generates a page fault because I create a new child and it's just full of nothings and I return it. So then I try and do a write to that same virtual address, which won't work. So in here, for this, it said it calls the page fault handler. So I just have, right now we can fix it. I could change the entry or do whatever. So yeah, and yeah, that's a good point. So for this too, whenever you do the copy, you shouldn't have to fix up anything in the page fault handler, because if a page fault happens and you made an exact copy of it, then a page fault should have happened, right? It didn't point to valid memory, it didn't have the right permissions, whatever. So this page fault handler fixing stuff up should only be applicable for the copy on write stuff. Okay, and yeah, sorry if any of this was unclear at the beginning. I thought I just kind of copy and pasted the MMU sim and thought everyone was good with it, but yeah, sorry, I should have probably documented it more, but hopefully this helps. So yeah, and it's not a lot of code. You should be able, if you don't do like 3 levels of for loops, it should be like 100 lines of code. All right, any other last minute questions, concerns, anything? I assume everyone will be working on it like Friday or over the weekend or Monday day? Yeah, Monday, yeah, okay. Yeah, I remember engineering undergrad, it was terrible. All right. Anything else? All right. Well, good luck. Pulling for you. We're all in this together.